send it back to Bob, who would then decrypt it, and TurboTax would learn nothing about the actual financial data of Bob. Okay, so what happens? So Bob, let's break that down again. Bob encrypts his data, so he has a bunch of numbers, data, M1, M2, up to M sub t. He encrypts it, or his computer encrypts it, and you get the ciphertext, the encrypted version. So that's C1, C2, up to C sub t. That gets sent to the cloud. The cloud has those ciphertexts. Suppose Bob, just simple computation, he wants to know M1 plus M2. If the cloud can add together the ciphertext C1 plus C2 and send it back to Bob, if it turns out that when Bob decrypts that, he gets M1 plus M2, then the cloud, then this works. The cloud just computes C1 plus C2, sends that to Bob, Bob decrypts it, and he figures out M1 plus M2. Same with multiplication. If the decryption of C1 times C2 is the same as M1 times M2, then Bob is happy, he decrypts, and he gets the product. That's what we mean by fully homomorphic. So homomorphic with respect to both addition and multiplication. Those of you in college or past college who have taken an undergraduate algebra course have seen the concept of a homomorphic function or homomorphism. This is why it got that name. So homomorphic with respect to addition and multiplication, and then you could do as many additions and multiplications as you like, and you can do your tax returns, for example. So this was presented as a problem or as an open question back in 1978, shortly after the invention of what was called the RSA encryption scheme. How many have heard of RSA? Great, so that was Rivest, Edelman, and Shamir. Rivest, Shamir, and Edelman, I guess. And two of those people were involved in this idea of fully homomorphic encryption. So what they said was, wouldn't it be really cool if we could do this, if we could come up with a way to do this that was both efficient and secure? That remained an unsolved problem for many, many years, until Craig Gentry made a significant step towards solving that problem in his PhD thesis in computer science from Stanford University in 2009. So for the first time, one could do an arbitrary number of additions and multiplications, at the moment inefficiently, but people since then have been working on more efficient ways to do it. So his solution was highly mathematical. It used something that some people call ideal lattices. So these are mathematical structures, and again, if you've taken an undergraduate university level course, you might have heard of ideals in rings, so that's where the word ideal is coming from. And they're also lattices, and I'll tell you a little bit more about lattices in a minute. Okay, so what's the mathematics here? So we want decryption to be homomorphic with respect to these two operations, addition and multiplication. What that means mathematically is you're taking something called a ring. If you're studying mathematics, this should give you some motivation to learn some more and learn about rings and algebra. So rings are things that have both addition and multiplication. Let me give some examples that you should be familiar with. So the integers. So 0, 1, 2, 3, 4, and so on, and -1, -2, -3, and so on. Those are the integers. Well, if you add two integers together, do you always get an integer?
No.
Yes. If you multiply two integers together, do you always get an integer? Yes. Okay, so the integers form a ring. That's an example of a ring. That's your basic example of a ring that you should keep in mind if you want to think of a nice ring. Another example, the rational numbers. So that just means fractions. So like 2/3, -7/8, 3, those are all rational numbers. If I add two rational numbers together, do I get a rational number? Yes. Yes? No? Yes?
Yeah.
How many people say yes? Raise your hand. Yes.